Welcome, everybody. Here we are. It's the July meeting of the Science and Engineering Council. Got a nice, good presentation about to start here. Just quickly introduce board members and our sponsors here and some new members. First of all, this is Tim Murphy here, co-president. We have Cheryl Ebner, Yvonne DeGraw, Mary Howe Grant, Bill Theringer, Joseph Stronks, Steve Skopatz, John Fishpaw, and if I miss anybody on the board, please, let me know. But we also have, I want to say hello and thank you to some new or recently renewed members, Harold Hill, Eric Ryan, Doug Troxel, and Robert Weber. I think one or two of us, you all may be on the call. You can kind of raise your hand or whatever you like to do, but thank you and welcome. Our sponsors are shown here on the screen: Community West, Bengal Engineering, Toyon, and Minot Enterprises. So thank you to our sponsors. Thanks also to everybody who donated for today's discussion and registering for this event. That'll really help with our administrative expenses and our science fair awards and other ongoing items. Okay, we'll keep it short there. With that, I'll go ahead and turn it over to you, Yvonne, to talk about upcoming meetings and introduce today's speaker.
Great, thank you, Tim. I just want to give people a heads up that our next meeting will be August 11th. It'll also be on Zoom. Our speaker will be Dr. Rajiv Bagrodia, who's the founder and CEO of Scalable Network Technologies and an emeritus professor of computer science at UCLA. He will be speaking on improving cyber resilience of mission critical systems with a focus on using digital twins to make networks more resilient. This includes systems used for 5G, information technology, critical infrastructure, and weapon systems. For future meetings, perhaps starting as early as September, we're looking at hosting in-person meetings back at the Frog Bar in Goleta. We'd like to simulcast those meetings over Zoom for people who aren't comfortable attending in person. If any of you have expertise with video, audio, and screen sharing of sort of hybrid meetings like that, please contact one of the board members. And today we're happy to present this talk by Lori Guetre, who is the VP of Business Development at Carbon Engineering up in British Columbia. So our speaker is pretty remote today, from us at least. Lori has spent the last 3 years working on commercializing direct air capture. She has previously spent 26 years in engineering, project management, corporate finance, strategy, and business development in the aerospace sector. Lori holds a bachelor's degree in computer engineering and a master's in electrical engineering. She's with us today to speak about direct air capture technologies along with carbon sequestration and utilization options. If you have questions during today's talk, you can type them into Zoom's chat area during the talk or ask them after the talk. So Lori, I'm going to stop sharing here. And you can share your screen.
Thank you so much, Yvonne, and thanks to the Science and Engineering Council for the opportunity to speak today, and to all of you for your interest in direct air capture and helping solve climate change. I've got some slides and really look forward to your questions as well. Lots on the go here as we figure out how to solve climate change. So just to step way back and look at the climate change problem, and I'm sure all of you know what's behind it, but just to level set, of course, the problem with climate change is greenhouse gases, and the biggest culprit is carbon dioxide. Since the pre-industrial level of 280 parts per million, we've been adding carbon dioxide up into the atmosphere. We found fossil fuels under the ground in the geosphere. We pulled them up. They were a fantastic source of instant energy and really cheap and abundant. But unfortunately, through the combustion, we add carbon dioxide up into the atmosphere. So we rocketed past that safe level of 350 parts per million onward to where we're at today at 417 parts per million. And we're adding about 2 parts per million per year, which is why you hear things like we have about 7 years left in the carbon budget before we hit 1.5 degrees. That's simply just some carbon math where we're adding 2 parts per million. And when we get to 430 parts per million, we're at about, on average, that 1.5 degrees. We're on track for rocketing past that 450 parts per million up to 3 or 4 degrees of warming. So we have a big problem with CO2 in the atmosphere. And back in 2018, the IPCC finally said, we're out of time. We need to reduce emissions everywhere we can. So we need to stop using fossil fuels wherever we can. But we're going to also need to add carbon removal. We're going to need to start to take carbon dioxide back out of the atmosphere, in addition to all of our efforts to reduce emissions, in order to get to that net zero by 2050 target. So that's the focus today, is how to reduce emissions and how to add a bit of carbon removal. But there are folks around the world also working on what would it take to remove that excess carbon dioxide from the atmosphere, permanently lock it away, and could we get back to that safe level? So first we need to get to net zero, which is an enormous challenge, but also it would be great to go backward and back off all of the impacts of climate change that we're already experiencing today. In terms of, what do we need to do? When I first joined carbon engineering, I said, well, direct air capture, that's a great technology. Isn't it nice to be able to vacuum some CO2 molecules out of the air? But is it relevant? Where does it fit in the big picture of solving climate change? Is it economic? Would we do this? How big would we have to build to be meaningful? And so I find it helpful to take a step way back and look at all of the solutions that are in front of us. What does it cost? And what kind of volume can we get from those solutions? And so what this is a typical abatement curve.
And we do that because of automatic vertex centration, cycle rotation.
There we go. So what this is an abatement curve. This one comes from Goldman Sachs. McKinsey does an abatement curve. There are lots of different abatement curves out there. I like this one from Goldman Sachs because it includes all of the data behind the curve. So you can go see an Excel spreadsheet with all of the data. And what it says is, today we emit about 53 gigatons, 53 billion tons of greenhouse gases, CO2 equivalent. What are all the different ways we can implement wind and solar and electrification? What's the volume of each of those on the x-axis? And what's the cost of each of those solutions? So where can we reduce so we don't emit? And then where can we also capture and remove the CO2? And so they included things like point source capture, so instrumenting a flue stack and putting that CO2 underground. They included electrification, low carbon fuels, what's the volume and what's the cost? And they came up with this curve. And this is today's curve. If we look way back to 2005, when the Stern Review was written, they had a different curve, and they estimated that it would cost about 1 to 2% of global GDP to solve climate change. But fast forward to today, this is the Goldman Sachs estimate for what it would cost. And you sort of see three key problems emerge when you look at this big net zero problem. What would it take? The first one is that the cost of carbon abatement rises to up over $1,000 a ton. And the area under the curve is 8% of GDP today, which is just unaffordable. Good that we know how much it costs, but 8% of global GDP is really hard to rally those resources. The second big problem is that we're not stopping at 53 gigatons of CO2 equivalent emissions. We're on our way to 80 gigatons per year in the business as usual curves. And then the third problem is that this is actually just today's emissions. And if we look at getting back to that safe level, removing about 1 trillion tons of CO2 versus the 50 odd gigatons of emissions today, that means that today's emissions are 5% of the problem, and all those legacy CO2 molecules that are still floating around us are 95% of the problem. And so even getting to net zero is the third big problem. So the net zero, the climate change problem is immense. We believe that DAC-based solutions are going to be really effective to help us get all the way to net zero, and then also to be a really cost-effective solution for transportation. And I'll go some more into that in my slides. Direct air capture, does it work? Does it work to vacuum CO2 molecules out of the air? Well, in fact, we've done so for decades. And if you're like me, one of your favorite movies is Apollo 13, because the engineers got to be some of the heroes in the story. And what popular science called the greatest space hack ever was a part in the movie where the engineers had to figure out a hack to start to remove CO2 from the capsule where the astronauts were, because they were building up a toxic level of CO2 in the atmosphere because of course we exhale CO2, and they weren't able to scrub. So they came up with an air scrubber using those traditional techniques. And we put people in spacecraft and submarines for years by scrubbing CO2 molecules from the air. What we didn't know how to do back when we were founded in 2009 was how to do that at really large scale, climate relevant scale, and at low cost. And when we were founded by David Keith back in 2009, he was an advisor to Bill Gates on climate. And so the story goes, Bill said, what's it going to take to solve climate change? And David said, well, somebody's going to have to figure out how to pull CO2 out of the air at big climate relevant scale. And to be able to do that, we have to get to low cost. It cost at that point in time between $600 and $1,000 a ton to scrub CO2 out of the air. And David said, I think we're going to need to get to $100 a ton to make it affordable. And so off we went with some seed funding from Bill Gates in 2009 to try to solve that problem. Could we get to a technology that would let us do that at large scale, low cost? And we decided to take a right turn off the path of the solid sorbent technologies that were being used at the time, because we could see that getting those materials in place to get to scale and also bringing the cost down was not going. We weren't going to be able to get there. So what we picked was a liquid solvent technology, a potassium hydroxide that I'll talk about in a few slides, and developed that, researched it, developed it, took lots of different paths along the way. And then in 2015, we implemented a pilot plant with the technology we had designed, which has been operational since 2015, capturing about a ton per day with the technologies that are in that plant. And what you'll see if you lift the hood and look at the plant is some off-the-shelf technologies. By design, we decided we needed to be able to go fast to solve climate change. And so we picked off-the-shelf technologies like calciners and air contact or air conditioning towers that I'll talk about in a few slides. We're just commissioning right now our innovation center, which is about 4 times the size, and up here in British Columbia, that goes operational this year. That will capture about 4 tons per day versus the 1 ton per day in the pilot plant. And that will be our permanent home for ongoing innovation. And we're already working on the generation 2, 3, 4 technologies that we'll insert into our direct air capture solution. And then this is a rendering of our project in Texas. This will go operational in 2024, and it's our final step up in scale to what has always been the design for our technology, which is to capture 1 million tons of atmospheric CO2 per year in a single project. That could be then the building block for what climate science experts say today that we might need, which is to remove 10 to 20 gigatons per year by the time we get to 2050. At Carbon Engineering, we see direct air capture as that technological missing piece to climate change, as the only solution that's available that's going to solve those 3 key problems that I was showing. So cost, it's affordable versus alternatives, and I'll go through some of the math. Goldman Sachs said it has the potential to be almost infinitely scalable. So it helps deal with that growth in emissions, and it can be a good backup plan to other solutions if they don't reach their targets. And then, of course, it helps us deal with that legacy CO2 because we're literally vacuuming CO2 molecules out of the air. And we're now deploying at commercial scale. So before I go into sort of where we see deployment and the economics, it's also useful to say, okay, if we can capture 1 million tons of CO2 or 1 billion tons of CO2, what are we going to do with those molecules? How do we put those molecules to work to make it economic to build out this clean infrastructure that the world's going to build out in the coming years? Well, this is an analysis done by McKinsey looking at what they call the technical potential of carbon capture, utilization, and storage in 2030. So what could you do, barring sort of economics and other constraints? And what they found was that the biggest place to put those CO2 molecules was what they called storage, which is geologic sequestration. So they felt it was technically possible to put about 36 gigatons per year into geologic storage around the world, into reservoirs. So that's good. That helps us with our 10 to 20 gigatons that we might need to do. And the next biggest place to put those CO2 molecules to work was into fuel. We can convert the carbon from the air into low carbon fuels like diesel and jet fuel by combining the carbon with hydrogen, making long chain hydrocarbons. So that's also a big important market for us. There are also other uses of the CO2, like putting CO2 into concrete to help put it into permanent storage, take it out of the active biosphere, put it into concrete, get it out of that carbon cycle. And so you'll see things like construction and biochar, enhanced oil recovery, plastics and chemicals, all being other utilization solutions. They're important to us. There are no policies today for putting a CO2 into concrete as a sustainable product or trying to decarbonize some of those sectors. They're important. They're less relevant to us when we're thinking about that 10 to 20 gigaton scale. partly because if we're building 1 megaton building blocks, then the concrete production typically needs much less than 1 million tons per year. And so it tends to be spread out, the production of these construction materials. So important to us, we're watching all of these, but storage, geologic storage and fuel are the two key markets that we think about when we look at what we're going to do with the CO2. So this is sort of how we show those two. Direct air capture is the new technology that we bring. Putting it into geologic storage is one of the ways we put it to work, and then taking that atmospheric CO2, putting it through fuel synthesis, combining it with hydrogen, making a low carbon fuel that's then going to go through combustion, and the CO2 is going to be reintroduced into the atmosphere. But now we're recycling or reusing the carbon in the air rather than having to pull new fossil fuels out of the ground and putting those through combustion. So we're helping to deal with the atmospheric CO2 problem. When we do a little bit deeper dive into the technology, so what did we put together? What you'd see within our plants is 4 key building blocks. And again, by design, what we did was we picked off-the-shelf equipment that was available at full scale, that 1 megaton scale in other industries, so that we didn't have to reinvent the wheel to create a new widget. We knew we couldn't get to climate relevant scale fast enough. We needed to use off-the-shelf equipment. And so what you'd find is 2 chemical loops. We have a potassium loop and a calcium loop in our process, and some 4 key building blocks that come from off-the-shelf technologies. So air contactors, which are just in repurposed industrial cooling towers, pellet reactors, which we've borrowed from water treatment technology, slickers for reconverting that calcium oxide to calcium hydroxide with water, and calciners, which are used in ore processing that let us heat up those calcium carbonate pellets and release the CO2. So off-the-shelf equipment. And then what we do is simply take massive amounts of air at the input. So CO2 molecules are about 0.04% of the molecules floating around us today. So we have to move a lot of air through the system to get to 1 million tons. Put them through the air contactor, put them in contact with a strong basic solution. So potassium hydroxide, which binds those CO2 molecules as they come through. That gives us this CO2 rich solution that we put into a pellet reactor, and we bring the potassium carbonate into contact with those carbonate ions and into contact with calcium ions. We do an ion swap, precipitate out calcium carbonate into little seashell pellets that we put into that calciner, heat them up to 900 degrees, release the CO2, and all the chemicals from each step go back and pick up some more CO2. So we reconstitute the chemicals from each step. So basically what it lets us do is fill the plant once, put the chemicals to work, and air comes in one end, pure CO2 comes out the other end, and then we're able to put the CO2 to work. In terms of geologic sequestration, so that first place where we're going to put CO2, it involves injecting CO2 deep into deep underground formations, such as depleted oil and gas reservoirs and saline formations. Atmospheric carbon is essentially evenly dispersed across the globe. And so we can put our direct air capture projects anywhere we have access to air and water and energy as an input. And so typically what you'd see for a DAC plant is that we want to put that DAC plant, somewhere near the geologic reservoirs where it's going to go underground, so that we don't have to build out pipelines or just a little bit of pipeline to get it to the sequestration site. There are over a dozen, I think there are probably several dozen projects operating around the world that are doing this today, where we put some form of CO2 back underground safely. If we look at where would we put that CO2 back underground, here's an image from the U.S. Department of Energy publishes what they call a carbon storage atlas, and they have inventories of where those saline formations and the oil and gas reservoirs. Where are they in North America, and what's the volumetric potential for those reservoirs to put the CO2 back underground? And the good news is that they're abundant. North America is blessed with these geologic reservoirs where we can put the CO2 back underground. And in fact, the US could offset its emissions today if we had enough direct air capture plants and not fill up its known reservoirs for over 500 years. So that's good, and that's why Goldman Sachs came up with the sort of terminology of essentially infinitely scalable, is that we have lots of time left to help us with the rest of the decarbonized decarbonization efforts, we can essentially put lots of that CO2 back underground. When we turn to the AirtoFuels pathway, so taking that carbon from the air and turning it into a liquid fuel, you know, it's useful to think about it as all fuels actually come from air, sun, and water as at the origin. When we look at fossil fuels, you know, produced over millions of years through the fats and biomass that were created originally from air, sun, and water. That's millions of years. Biofuels, when we create those from those bio feedstocks, that takes weeks or months. With our AirtoFuel solution, we're simply doing that same process across the span of hours. So taking the carbon we captured from the air, putting it together with hydrogen through fuel synthesis, and making a synthetic crude that can then be turned into those finished products. Looking at sort of in more detail at an AirtoFuels plant, you know, producing green hydrogen, we implemented this process in 2017 up at our pilot plant, and green hydrogen and fuel synthesis for us were essentially off-the-shelf building blocks that we felt it was important to combine with our DAC technology to prove out the technology at end-to-end operation, and also prove out our techno-economic analysis. But we took an electrolyzer, produced some green hydrogen by splitting water into oxygen and hydrogen. Then we take that hydrogen, put it through a Fischer-Tropsch system to create the fuels, and we produce drop-in compatible fuels like diesel or jet fuel. And the valuable thing that's in our fuel is what you can't see in this fuel here over on the right that's clear, which is the low carbon intensity. And that's what earns credits in markets like the California Low Carbon Fuel Standard. But it's interesting to note that we also bring co-benefits like clean burning, so we don't have particulates, you don't see the soot from the diesel, fossil diesel that's burning here on the left, no sulfur, so we don't produce sulfur oxides. So there's an air quality benefit that comes from burning these synthetic fuels, as well as that low carbon intensity. When we look at deploying these AirtoFuels projects, we call it, we're actually harnessing not just our new DAC technology, but all of the work that's being done in the hydrogen economy to on electrolyzers and other clean hydrogen production. There's a build out of low cost renewable power, lots of advances in wind and solar, which we get to use, and then advances in those fuel synthesis systems as well that help us create those fuels. And of course, there's a reason why we use liquid fuels today is that they carry a really high energy density. We have this, you know, global transportation network to move liquid fuels around. So they're really valuable still in helping to decarbonize sectors like aviation, where we need to still use liquid fuels. We actually have about 100 times less land use than a biological solution, a biofuel, and about 200 times less water use when we create the fuel this way. So that's important where we have land and water scarcity. And of course, this is also highly scalable as well. So when we then put this all together and we say, okay, what role is direct air capture going to play in helping to solve climate change? If we have scarce resources to solve climate change, which of course we do, and we need to go quickly. This is a look at what happens to that abatement curve that Goldman Sachs had drawn previously without direct air capture. Now we just basically draw a line across the cost of solving climate change. So with direct air capture and sequestration at $150 a ton, the first project costs more than $150. Future projects will cost less, $100 and we think below. But if we just draw the line across at $150 a ton, this is what it looks like. So it means that we could cap the cost of getting to net zero, and the world would save over $3 trillion per year versus today's known alternatives. And hopefully we come up with lots of other good alternatives as well, but this is a meaningful, huge potential savings in implementing this technology. That would be about 10 gigatons per year. So that's consistent with what climate experts are saying. We're going to need to do 10 to 20 gigatons of carbon removal through direct air capture in addition to everything else. When we decrease in cost and we're down at $100 a ton, that line drops, and we're actually useful for about 50. We're cost effective, least cost solution for about 15 gigatons per year, and then we're also a good backup plan for anything else that doesn't reach the scale or cost targets. And then hopefully we get to net zero, and then we're part of the solution for drawing down that legacy CO2 as well. Just another quick look at that first commercial DAC plant. So thanks to California, thanks to the California Low Carbon Fuel Standard, and the California Air Resources Board that back in February of 2019 said that the low carbon fuel standard had previously been trying to motivate the creation of low carbon fuels so that we could avoid putting a ton of new carbon into the air. The California Air Resources Board said, okay, now that direct air capture technology is maturing and ready to commercially deploy, now that we can take a ton out of the air and permanently remove it, we're going to expand the policy to allow for that to earn LCFS credits directly. So California has the world-leading policies on decarbonizing. California made that announcement in February of 2019 about the policy change. And in May of 2019, we announced that we were going to move forward with the front-end engineering and design of our final step up in scale to that megaton plant to serve the California market. This is a rendering of the engineering model for that plant. We're now over 65,000 person hours into the design of that plant. And our partner in the US for that is a company called 1.5. And the sequestration partner is Oxy Low Carbon Ventures, who are experts in the handling of CO2 and the permanent sequestration of CO2 back into the geosphere. When we think about, just a few slides on the California context, when we think about where the state is at, of course, not just world-leading policies in decarbonizing, but also huge public support and a state-level ambition to get to net zero. We look to not just the California low carbon fuel standard that aspires to create 30 megatons per year of benefit, 30 million tons per year through low carbon fuels and carbon removal, but also an analysis that the Lawrence Livermore National Lab did recently that said, okay, we have California as a state has policies in place to get 80% decarbonized. Where should we get the remaining 20% from? And so they did an analysis of all kinds of different ways in a report called Getting to Neutral. And the conclusion of the report was that California should look to an additional 16 million tons per year as part of filling in the remaining 125 million tons that would be needed to get all the way to zero. So we were really excited to see that as part of their thinking. And also in parallel happening right now with announcements coming out every day is that an organization called Breakthrough Energy, led by Bill Gates and others, have picked 4 critical clean technologies that they think need to go to scale to help solve climate change. And they've picked direct air capture, green hydrogen, long duration storage. So how do we put the wind and solar energy into longer duration storage so that we can use all those green electrons and not have to curtail the projects. And then sustainable aviation fuel is the 4th one. So those are the key technologies that they think need to get deployed at scale. Of course, direct air capture using long duration storage uses 2 of those. And then when we look at AirtoFuels projects, that's all 4 of those clean technologies put together into one. So we're looking at AirtoFuels projects in California. In addition to the direct air capture sequestration, the reservoirs in California that the Lawrence Livermore Lab had identified for geologic sequestration will be good, but they will need several years of work to create, to categorize the reservoirs and make sure we're going to implement projects for sequestration that are safe in the California reservoirs. So in the meantime, we've been looking at where can we put AirtoFuels projects in California. Of course, as we mentioned, you can put a project anywhere. We have access to air and water and energy. We also have to, in that case, think about the offtake. Where does that sustainable aviation fuel go? To a refinery and off to the airports that will make use of it to help decarbonize aviation. One of the things that the Lawrence Livermore report said is that not only can California get all the way to net zero through these different technologies, but California has the ability to create those jobs at home. So all of those projects that were recommended could actually be built in the state with the resources that are available. So similarly, we're looking at how could California create those clean infrastructure projects at home. And we're engaged with the state looking for a little bit of support to get going with those projects. As we look broadly across the globe, we're driven by a couple different things. Where are the carbon policies and the desire to do that good? And also where are the least expensive, highest, strongest economics to build out those first few projects? So we started in West Texas, partly because wind and solar are really inexpensive and there are already those reservoirs that are identified. But we'd love to help see some of these projects come online in California, positioning California not just at the forefront of the build out of the direct jobs that come from these, but also the ecosystems for the equipment that will supply these projects, and also the offtake, so the utilization of the CO2, whether it's into fuels or into concrete or into those geologic reservoirs or other utilization solutions. At Carbon Engineering, we think that direct air capture will help us with, to restore the carbon balance through sequestration and utilization, help us as an all of the above approach. The world needs to be doing everything we can to solve climate change. We just need to add this in addition to wind, solar, afforestation, land use practices, electrification. All of those are really key. This is just the missing piece that will help us get all the way to net zero. In the short term, we'll be producing fuels to help with those hard to abate, hard to avoid emissions like from aviation as we achieve net zero. And then in the longer term, hopefully we're removing that legacy CO2 so we can restore the climate back to those safe levels. And that was it. Mark Carney famously said, achieving net zero could turn an existential risk into the greatest commercial opportunity of our time. We certainly see it that way and would love to work with jurisdictions that are thinking about how to implement climate solutions. And happy to answer questions.
Great, thank you. Let's see, so I'm going to open it up to questions. We have one from George, who asks, has the fossil fuel industry shown any interest in this technology? Are they funding any work on it?
Great questions. Yes, and in fact, so in early 2019, we announced that Oxy, Low Carbon Ventures, Chevron, BHP were actually all investors. So they brought money into Carbon Engineering. And why? You know, where are all of these energy companies at with their thinking about the energy transition and the role that the company is going to play? I would say as we engage with the energy companies, there's a big spectrum. Some are hoping that fossil fuels last forever, and some are thinking, you know, fossil fuels have 10 to 20 years left, and we better figure out how to be part of the energy transition. And I would say, you know, our collaboration with Oxy Low Carbon Ventures has been this end of the spectrum. If you listen to Vicki Holland, the CEO of Oxy, on her earnings calls with her shareholders, more and more she's talking about Oxy becoming a carbon management company. So they happen to have an expertise where a lot of their work was actually taking CO2 and putting it back underground for enhanced oil recovery. So they had a lot of experience with that. And that let them sort of be at the forefront of thinking about, well, you know, when we put the CO2 back underground, if we take atmospheric CO2 and put it back underground and keep it underground, that's actually a net benefit to the climate. And, you know, as the market comes online for pure sequestration, so starting to take just CO2 and putting it underground without the production of fossil fuels, that's also going to be a market that's really important as we go through the energy transition. So certainly that's a public company that's talking about it. I would say all of the sort of energy majors that have had experience with CO2 sequestration are toward this end of the spectrum. Others that perhaps are European-based and don't have that experience with putting CO2 into geologic reservoirs are thinking more about the conversion of atmospheric carbon to a low-carbon fuel. So AirtoFuels projects, sort of more in Europe in terms of not being blessed with the same geologic reservoirs to put the CO2 underground. So from our perspective, we're a small technology company that's built a direct air capture technology, a tool in the toolbox. We need to work with experts in sequestering CO2, converting CO2 to fuels. And so we see that there's a huge role that the energy companies could play in the future. We're super excited by those that are really taking meaningful action today to make that part of the energy transition.
Great. We have a couple of questions about the energy cost or the energy budget for capturing carbon.
Yeah, so energy costs. So in our process today, we use a combination of renewable energy to power the plant, and then there's one step in our process, the calciner, that we still use natural gas for the thermal energy that we need in the calciner. And when we use renewable energy, you know, West Texas wind is coming in at about $12 a megawatt hour. Solar is coming in at $20 or $21 a megawatt hour. So really cheap, abundant, untapped wind and solar energy there, and really low pricing. So that helps. When we use natural gas in our process, what we actually do is we oxy-fire the calciner. So oxygen in the process, when the CO2 gets released from the pellets, we actually, because we're oxy-fired and the calciner, we're actually capturing the CO2 from the combustion of the natural gas at the same time. And then all of that CO2 gets sequestered. So when we look at the life cycle analysis, so we measure air to rock, how much net environmental benefit did we do? We take very little hit for the use of natural gas in the process because we simply re-sequester the CO2 from the combustion along with all the other CO2. And so the net project really doesn't take a hit for that. When we look at converting the fuel, the atmospheric CO2 to fuel, we don't get that same benefit. So we're not re-sequestering the CO2 from natural gas. So the life cycle analysis carries some of that fossil CO2 hit in the carbon intensity of the fuel. We produce a fuel at about 30 grams per megajoule when we use natural gas in the process, which is still really good. So if fossil fuels at 100 grams, biofuels are kind of in the range of 30 to 60 grams per megajoule. We're 30 grams per megajoule when we use natural gas. And we're working on an all-electric calciner as well, so that we can actually take the 30 down to 10 grams per megajoule. So ultra low carbon intensity fuel. And the way the economics work, it makes sense to use natural gas for the DAC sequestration projects, and it makes sense to use an all-electric calciner for the AirtoFuels process. In that case, we would just use all renewable energy like wind and solar.
Great. Does anyone want to unmute themselves and ask a question, and then I'll mix in questions from the chat with that?
Hi,
Robert? Okay, go ahead.
Yeah.
Hi.
Yeah, I mean, to me, this is really wonderful from a technological standpoint. But to me, the elephant in the room is how do you get some kind of carbon tax or cap and trade system in place? What do you know about that?
Yeah, so it's already in place. So the good news for us is that, and again, it's with California's pioneering leadership, that the combination of the 45Q tax credit and the California low carbon fuel standard credit, the combination of those makes it economic for us to go forward. So that's why we're all that way 65,000 person hours into the front end engineering and design of that full scale project, is because of the combination of those two things. So the good news for us is that we're and that's the hardest project. Of course, the first one's always the hardest to build. So it's economic, and it's because we're decarbonizing transportation and cost effective in that space. When we look at ETSs and other policies to decarbonize power and industry, what you see is much lower. So the California ETS trades at a much lower credit price. The European ETS, I think, trades at about 55 euros per ton. But in the California low carbon fuel standard, the credit's traded about $200 a ton. Elsewhere around the world, the UK development fuel credits traded about $400 a ton. So the policies to decarbonize transportation, given that a biofuel costs about $650 a ton, tend to come in, more than high enough to make our projects go forward.
Yeah, but I got that about California, but that still leaves out huge parts of the world. I mean, like most of the world.
Yes, yeah, no, for sure. So what's happened since California made that pioneering change is that the Washington State LCFS, Washington State passed their legislation, and the Washington LCFS includes DAC sequestration, just like California did. Up here in British Columbia, where I am, the BC LCFS is expanding to include DAC sequestration. Across in Europe, Germany, Sweden, and the UK all have carbon intensity based fuel policies like California, which sets the stage to also allow DAC sequestration. So we see that, and there are also governments, for instance, there's a bill that was proposed in the US federal legislature to do just carbon take back. So just a direct procurement of negative emissions by the government to decarbonize the government footprint. And that's happening in the UK and elsewhere as well. We're also seeing the voluntary market stepping in. So we're seeing companies like Microsoft, Shopify, others just directly procuring carbon removal from companies like us. We announced that the company Shopify procured 10,000 tons of carbon removal from us. And what companies are doing, and more climate experts are telling us, is that planting trees is good, and we need trees for lots of reasons, ecosystems, reforesting, that kind of thing. But trees that we thought were sinks before are becoming sources of carbon. And so it's not good enough to just plant trees. We also need to get to more durable storage and ultimately to permanent removal of the carbon from the active biosphere. We need to shift across there. And so what we're seeing is that these thoughtful companies that have climate teams actually do all of their own analysis and come up with the same conclusion. The world needs to work on permanent carbon removal. And so we're gonna, you know, in advance of being required to do so, we're just gonna voluntarily buy carbon removal. And Microsoft aspires to ultimately source 6 million tons per year just for their own carbon footprint. So we love that. That's helping accelerate the pace, the raising awareness, global awareness, and also accelerating the pace at which we can build out these projects in the voluntary market while the government regulations catch up.
Just a quick question. First, it was a great talk. I wonder if it will be available for others to listen to after this.
Yes, we're recording it and we'll put it on YouTube.
Very good. So the technical question is, what is the diffusion timescale like, so that if you were to remove carbon from the lower atmosphere, you still have carbon, you know, far above you? Have you looked at the sort of life cycle of carbon in the atmosphere and the timescales for mitigation?
Yeah, the good news there is that of course, the atmosphere is moving around us all the time, and it's actually redistributing itself. Even point sources of carbon, of course, get dispersed quite quickly. And you know, essentially anywhere on the Earth that you go, you'll be within a small range of that 417 parts per million, a little bit closer to the urban, a little bit higher, closer to the urban centers that are producing more, but it disperses itself really quickly. Even if you went and measure the carbon dioxide concentration right next to one of our projects, we remove about 75% of the CO2 from the air through our process. And so the output from the fans has just only 25% of that normal concentration in it. But you go a few hundred feet away and you're already back up to 300 parts per million. So the atmosphere is just redistributing the carbon all the time, all around us. And so that lets us put one of these projects anywhere and do the benefit. So what we're starting to see is, you know, companies looking at, Microsoft said, I'm emitting over here today, remove carbon over there, and that counts toward my decarbonization because the atmosphere just keeps redistributing. The California Low Carbon Fuel Standard policy actually allows for carbon removal to happen anywhere on the planet, as long as the environmental benefit is retired on behalf of the California Low Carbon Fuel Standard, because the atmosphere is a shared resource and we're just redistributing that carbon. Microsoft's also thinking about that legacy CO2. So they were the first company to announce that they would not just go true net zero. So for every ton that they emit, they would remove a ton of carbon, but also they wanted to go backward in time and remove all of the CO2 molecules that they emitted since they were founded, because CO2 molecules stay in the atmosphere for hundreds of years. So they wanted to do that cleanup of their legacy carbon as well.
Yeah, I guess the question is maybe a more technical one. Have you run an atmospheric model where you have point source removal at low altitudes, and then you look at the sort of the entire atmosphere, both the absorption, so you do a radiative transfer problem, and look at point source removal, or, you know, moderately localized removal, and then see what happens to the Earth over time?
Yeah, so, and I'm not an expert in that aspect, but from what I've read, the generally it's just redistributing itself because the Earth is spinning and the atmosphere is recirculating so quickly.
May I ask you a question? What is the cost of the absorber part of the installation? Is it the 50%, or what is how much is it?
Yeah, it's a potassium hydroxide basic solution that we created, that wet front end. And we chose it because it's cheap and abundant to make. So it's a pretty inexpensive part of our process.
That's in potash?
Sorry, say again.
The installation itself, is it the plates and the ventilators? How much do they? What is how is it in respect to the total cost?
Yeah, actually, I should have mentioned when I was on that slide, I'll just throw the picture up again. On that slide, I included a link to a paper that we published in a journal called Joule back in 2018. And we Carbon Engineering, we're the only company to have published a detailed techno-economic analysis of our technology. We published it back in 2018, and I included a link. I'll just show you one more time on the lower left-hand corner, or if you just Googled Carbon Engineering Joule, you would get the link to the paper that we published. And what you'd see if you look at the paper is quite a detailed CapEx and OpEx breakdown and a much more detailed discussion of our technology. And what you see is the first plant costs about $1.2 billion in CapEx. And then we show first plant and an nth plant, and we show a couple different combinations of our technology, combinations of natural gas and renewable energy. So, you know, I guess the real question is why did we, as a company trying to commercialize our new technology, why did we publish such an open look at our technology and the costs? The answer back in 2018 was because the world still felt that it was $600 to $1,000 a ton to remove carbon from the air, and we knew it wasn't. And we felt to go fast, we needed to be public about it so that we could get peer-reviewed scrutiny on our technology and the costs, so that the world could see the same picture that we saw, which was we're ready to go, we're ready to commercialize, and here's how and why you can believe that it's possible to do this. So we published it, and then that's when we brought in those major investors and announced soon after that we were moving forward to commercialization.
Okay, thank you.
Hi, can I ask a question?
Yes, go ahead.
Hi, have you considered sequestering carbon at the source, like near the power plants where the concentration on the exhaust is the highest? So that would reduce the cost of separating the carbon dioxide from the air.
Yes, absolutely. So the world it's not, carbon engineering is not working on that, but there are many companies that are working on point source capture. So scrubbing the flue stack of for instance, a power plant where the greenhouse gases concentration is much higher. So how do they scrub the CO2 as an emission reduction technology? So the power plant is burning fossil fuels, but how do we capture that and then sequester it so that we reduce the net emissions that come from that fuel combustion? There are many companies working on point source scrubbing technologies, and many organizations looking at exactly that. How do we instrument those flue stacks, pipe the CO2 to a sequestration site? And what we're seeing in the infrastructure package is that countries are looking at clusters. So how do we take a whole bunch of point sources and get them pipelines to a CO2 sequestration site? Our project developer over in the UK, for instance, Pale Blue Dot Energy Storega, is looking at one of the UK clusters where they would take all of those point sources, add direct air capture on top of it, and then use that common sequestration site for all of those different sources. Point source capture is another really important part in all of the above solutions for solving climate change. Absolutely, in cases where it's economic to and less expensive than direct air capture to do that, we should be doing that. Some of the challenges that come in is that not all of those point sources are near a sequestration site, and creating billions of dollars of pipeline infrastructure is another piece of the puzzle. So you have to kind of look at the blend of where can they make it work, but definitely it's important. But it's not what we're doing. We specifically focused on that different challenge of a separate but important challenge. How do we scrub CO2 out of the air as well?
Thank you. I had a follow-on question, if you don't mind.
Sure.
So what is the ratio of power generated versus power consumed? So for instance, if I'm generating a ton of CO2 and generating, say, 100 megajoules of energy, how much energy would it take to take that carbon CO2 and put it back into the ground?
Yeah, so the paper, the Joule paper, will give you lots of detail on the energy input requirements for the direct air capture piece. Of course, then there's a sequestration piece, which is a small component, but an important piece of the energy used to put the CO2 underground. It is an energy intensive process. So we're scrubbing CO2 molecules out of the air. So lots of energy input, which is important. But the aspect, and I heard somebody yesterday talking about, well, we would need as much green, clean energy as the US is currently producing to be able to remove all of the carbon that we need to. So, what's important about the deployment of direct air capture technology is that if you talk to any of the wind and solar developers across the US, they tend to have built out, and for instance, in West Texas, they're standing at the start line with all of these additional resources that they could build out, but nobody to buy the power. And so what we do is we come along with a direct air capture plant and we say, you know, we need 110 megawatts of clean energy, and the wind and solar producers say, great, we can now build out those additional wind and solar projects to support you, because you'll be a committed off-taker for clean energy. So because we can put direct air capture projects, you know, we have lots of location flexibility. We can go to the places that have the right combination of additional wind and solar resources that we can build. So it's not to say we're very energy intensive to do that process, but it's cost effective, and we're not limited by taking green electrons from somewhere else, or limited by the amount of build out of those additional renewable resources. They're essentially unlimited in terms of trying to help decarbonize.
And you can also do it during off-peak hours, right?
Yeah, so we're really excited about, I mean, there's a whole parallel track on the clean hydrogen economy coming that's looking at hydrogen for lots of things, including the use in a low carbon fuel like ours. And so as clean hydrogen, our calciner heats up to 900 degrees. It wants to stay there at 900 degrees. It doesn't want to cycle, but hydrogen electrolyzers can cycle within minutes. And so the potential to take all those green electrons when they're available, create hydrogen from it, store the hydrogen, is great. It'll be a piece of the puzzle. You know, hydrogen vehicles will be a piece of the puzzle, but then taking that hydrogen that we can use those from those green electrons and turning it into a low carbon fuel, and then having that diesel or jet fuel just be part of the transportation.
Really comes in and whatnot. I don't know if Matt's in here. Okay.
Thank you. I was just curious on the whether there was a ratio available, like 110% or 15%.
We're just essentially removing carbon. So all of the energy has been used to just put the carbon back underground, but the Joule paper will give you lots of those details.
Okay, thank you.
Right. We had a question asking what the projected cost of diesel per gallon would be.
Yeah, so more expensive than fossil. So low carbon fuel that's created through this process is fossil fuel will probably always be the very cheapest way to get the fossil energy. The problem is it comes with the pollution at the same time. And the other thing that's being considered is to think about the cost of abatement in a dollars per ton rather than just the volumetric basis, so cost per gallon or cost per liter, because each of the different kinds of fuel is different in terms of the carbon intensity. And so when we look at it on a volumetric basis, we don't quite see the full decarbonization benefit that comes through. So if you look at, and if you looked into the Goldman Sachs data, that's exactly what they've done. They've looked at the cost of all of the different synthetic fuels and biofuels. And that's where they said, you know, the cost of decarbonizing through biofuel is about $650 a ton. The cost of our first project is economic at about $300 a ton for DAC sequestration. Fuel is more expensive. Like if you're an airline and you look at decarbonizing in California, you can, and the policy allows for DAC sequestration and a low carbon fuel, and we can create both of those. And you're an airline and you want to decarbonize, and you have both of those tools in the toolbox. The next question is, which one costs less? And the answer today is that it's cheaper to decarbonize through DAC sequestration than it is to create a low carbon fuel from air, just on the cost of abatement. But we see AirtoFuels has a role in lots of different places where the air quality benefit is important, or you don't have the geologic reservoirs to put the CO2 underground, but you want to have the jobs at home, or you know, public support is just wanting to burn a sustainable aviation fuel. So we even though, and it's economic in some of the fuel policies over in Europe today. So we see the build out of AirtoFuels, which is more expensive, and DAC sequestration happening in parallel. And then we actually see the cost of our low carbon fuels reaching parity with the DAC sequestration over time, because our inputs, instead of like a biofuel where the feedstocks are limited and the costs go up over time, in our world, the cost of wind and solar gets cheaper, the cost of green hydrogen gets cheaper, the cost of fuel synthesis gets cheaper, and the cost of DAC gets cheaper. So our AirtoFuels process actually gets cheaper over time, and we think basically reaches parity with the cost of DAC sequestration. So we work really hard at having both of those technological tools in the toolbox, even though the cost is different today.
Hey, other questions?
Yeah,
Yeah, this is Matt.
Sorry, this is Peter Lombroso. Did you see the article in the Scientific American for this month about the sequestration of this special mineral they found in Oman that can has a potential for trillions of tons?
Yes. So mineralization of atmospheric CO2 is a potential. When we look at all the places we're going to put the CO2, get it out of the active biosphere, mineralization into rock is one of the really important things that's being looked at. And mafic, ultramafic rock is abundant across the U.S. And in fact, there are some states that don't have any geologic reservoirs, but have mafic rock that are looking at how can we put projects to work there. There are experiments that are being done, sort of demonstration scale things being done across the world. In some cases, it's mining companies that are looking at crushing up the rock in mine tailings and exposing that rock to the air. Actually, they're doing some mineralization. So they're actually doing some good that they hadn't realized in terms of pulling CO2 out. And so they're looking at that. There are projects like the CarbFix project in Iceland that Climeworks is working on, where they take CO2 out of the air, basically create carbonated water and inject that carbonated water into the volcanic rock, and some of that CO2 mineralizes. So there's tons of potential there. The challenge in the mineralization space is cost. It's also, the standard to which we're going to do the work. We don't have standards for that yet. We have standards, government and ISO standards that let us measure the benefit that we did with the geologic sequestration. In the world of mineralization, we don't have those standards yet that let us measure how much environmental benefit did we actually do, how much of the CO2 got mineralized, and how much just bubbled back up again. So probably within the next 10 to 15 years, we will have standards, and mineralization will hopefully have a huge potential to be part of the solution for what we do with the captured carbon.
Thank you very much. Yeah, that sounded really great to me when I read that.
Matt, were you trying to ask a question?
Yeah. So you're saying that the engineering you're doing is financed by investors for the California marketplace, but you haven't had certification of this scheme, right?
Yeah, so the way it works for the California Air Resources Board is that a pathway is fully sort of validated and approved once the project is actually live. So we design to all of the different standards in the California regulations. And then once the project goes live, the final assessment and the pathway approval happens for, in this case, a DAC sequestration project. And it has to comply with the California CCS protocol if it wants to earn a California LCFS credit. And that includes the GREET model and the assessment of the air to rock, so the full life cycle for the project, and then net environmental benefit that's done. If
Okay,
we,
so,
yeah, go ahead.
So I hate to be a curmudgeon here, but lots of schemes, and you identified a price, 150 a ton. That's fine. I understand that, but carbon sequestration hasn't been finally approved by the federal government or the California government. Let's assume the federal comes first with approval. I would assume that you would put your first facility in West Texas and get the credits that way. Is that?
Our first project is in West Texas, and why West Texas is it's simply because the first one is hardest to do, and we have to go where the economics are strongest to let that happen. And so West Texas just has abundant wind and solar. We have a good partner, 1.5, who will do the sequestration, our licensing partner, and the geologic reservoirs are ready, and the CO2 pipelines are there. So it's just sort of a critical mass of the best elements to let us do that hardest final step up it to full scale. But the standards, just to be clear, there are standards. There's an EPA standard for geologic sequestration, the California CCS protocol. Up here in Canada, Alberta has a CCS protocol. Our project developer, Storiga in the UK, would have to comply with the offshore sequestration and the government regulations from the UK for geologic sequestration. And then there's also an ISO standard that's been developed over the last few years for geologic sequestration, taking all of those bodies of knowledge from the other work that's been done in a global group, as with any ISO standard. The ISO standard is not being used by anybody yet, but of course the world will gravitate there as we always do when we create an ISO standard. And then there are also, we're working on a standard for the voluntary market as well that takes, again, all of those bodies of knowledge and creates a voluntary market version of it, because ultimately if we're providing carbon removal to Shopify or Microsoft or others, then we need to do it under a voluntary standard that's not a government employee that's overseeing the work, but the same sort of body of knowledge instantiated in a voluntary standard. So in the world of geologic sequestration, there are projects happening all over the world for doing geologic sequestration. Those are the reservoirs that will take most of the CO2, but then hopefully there's mineralization and all of these other concrete and all these other ways that will put CO2 to work, as well as those geologic reservoirs.
Okay, well, thanks.
Yeah.
You're very knowledgeable. And do you have contact information if I had some follow-up questions?
Absolutely, yeah, I'd love to follow up. Yeah, so Yvonne has my contact info.
Okay, thank you.
Hal
Hi.
had a question.
Yes, can you hear me okay?
Yes.
Okay. I'm interested in collaborating, Lori, because we may have the right combination in North County and Santa Barbara County, because we're gearing down for the oil operation up there, and we have the manpower to drill for sequestration. And we have under construction right now a wind farm operation that's going to create some attractive energy costs. What can we do to kind of analyze the feasibility of doing a project in North County, Santa Barbara?
Please reach out to me. We'd love to follow up and talk some more. So, so you bring up a few really good points that I hadn't mentioned. One of them is, you know, in the energy transition and the climate justice, environmental justice area, one of the really useful things we bring to the table is that we create jobs, and often those jobs can either you know, the folks in the energy industry today have the skill set that will be really helpful for us to implement these projects, whether it's sequestration or production of a synthetic fuel and the refining of that. But we also have that location flexibility. And so we see politicians looking at the potential to create good jobs in areas that have the workforce and maybe are going through, you know, phasing out of other industries and can build out this new clean infrastructure and be, you know, one of our plants is designed to operate for 30 years. So we create lots of good construction jobs, lots of good steady state jobs operating the plant. So, so definitely love to look at locations that have some of those great resources to produce either low carbon fuels or sequestration, or, you know, we can take a 1 megaton plant and turn, you know, 200 kilotons into fuel and put 800 kilotons a year back into a sequestration site. So we can actually split the output of the captured CO2 into multiple things. So yeah, please follow up. I would love to explore further the potential for projects in your region.
Thank you.
Hi, hi. This is Momin Kudus. I work for JPL, and I wanted to add to the argument of building a carbon sequestration plant in West Texas. We had done a study a few years back in the West Texas where there were sinkholes appearing, and it turned out that the sinkholes were appearing because of the oil caverns. That oil was removed from underground, and it created caverns which were collapsing. So, so this would be a good way to fill up those caverns so they don't collapse and create giant sinkholes.
I am not a geotechnical expert or a reservoir expert. My understanding, and I actually came from an aerospace company that was monitoring ground deformation from injection underground as well. So lots of different technologies to bring to bear on this. In terms of the reservoirs that are good reservoirs to do this sequestration of CO2, definitely not all reservoirs are created equal. Some of them have too many pinholes. You can't guarantee that the carbon will stay underground because they were built out in the 70s, and the wells that were drilled at that point in time just can't, the integrity of those wells can't be trusted, or there's a fault line through the reservoir or something else. So my understanding of sort of what happens in the reservoir space to make sure that when we do a sequestration project, we know that the CO2 stays underground is that all of that reservoir categorization has to be done in the geotechnical work, which is why those ones that were identified by the Lawrence Livermore report are going to be really important, but need some of that more homework. whether or not we could take those ones that are deforming and it would be a smart thing to put the CO2 back underground. I'd need to look to those experts who understand their reservoirs. But yeah, CO2 repressurizing, I mean, that's what enhanced oil recovery is repressurizing a depleted reservoir that still has oil and gas in it, repressurizing it with CO2, and typically a CO2 and water flood is exactly what they do with enhanced oil recovery.
Any more questions? Well, this has been a great talk. I've really enjoyed it, Lori, and I think a lot of other people have. So
thank you so much for your time. Really appreciate your interest. And please, Yvonne, please feel free to share my contact information, and would love to follow up with anyone who's interested in the technology or in projects in your region.
I will do that.
Great.
So it's been great to see everyone, and we're looking forward to seeing you again at our August 11th meeting. Thank you.
Thank you.
Bye. Thank you.